So last week we have gone through until actually this part. Yeah, this part. Yes, we haven't go into intermolecular yet. Right, so I'll go from this part first. The previous part you can view the recordings, right? It's still manageable for previous parts. Yeah. So next, we talk about the strength of covalent bonds, what is affected by. So there are three factors which affects your covalent bond strength. The first one, okay, it is your effectiveness of orbital overlap. So if you can see from the example, you have F-VEF bond and II bond, right? So you should have learned from the atomic structure that for FF to overlap, it involves what orbitals? For FF bonds, you involve what overlap? FF bond. Now that you have learned your hybridization, correct? Take note, chemical bonding is before the chapter on hybridization, correct? So at this point in time, students don't explain it in terms of your hybridization yet. But of course, you can explain using both ways, right? So if let's say you explain using the without hybridization explanation, right? What orbitals will be involved? 2p orbitals, right? So you have a 2p overlap. Okay, what if you involve your hybridization? Is the overlap between what orbitals? What's the hybridization state of fluorine?
Is it SP?
SP? What was your answer?
SP.
Also SP?
Wait, SP2.
Remember what we learned during intro to organic chem. Okay, how do you determine whether it's SP, SP2 or SP3?
The hybridized orbitals.
Yes, you can count the number of lone pair as well as the number of bond pair. Remember? I clearly remember that in my intro to organic notes I have a table, right, which tells you that as long as I have as long as I have a lone pair, correct, what I'll involve is a hybridized orbital, which looks like this. This is hybridized. As long as I have a sigma bond, one sigma bond, I'll have one orbital which is hybridized like this. Okay, and as long as I have one pi bond, I will have an orbital like this, but it's unhybridized. And afterwards, I clearly remember that I have another table which tells you that you just have to count in total how many hybridized orbitals I have. So for example, like this case, how many lone pairs do I have on fluorine? This is the structure of fluorine, right? So for this fluorine, there's 1, 2, 3 orbitals. Sorry, 3 lone pairs. So I have 3 hybridized, these kind of orbitals. 3 are hybridized. Followed by a sigma bond, which must be like that. Correct? So in total, I have 1, 2, 3, 4. 4 means it is sp3, if you refer to my table. Right? If it's 4, it will be sp3. If it's 3, it will be sp2. If it's 2, it will be sp, and so on. Correct? You can refer to the notes. So now, for this case, we know that the hybridization state is sp3, correct? So it will be a sp3 overlap. And then I ask you, this S is what S? 1S, 2S, 3S? And this P is what P? 1P, 2P, 3P, 4P? It's the valence orbitals, correct? So for fluorine, this S will be 2S. This P will be 2P. Correct? That's for fluorine. If you were to look at iodine, right? Without hybridization, what orbitals are involved? How many P? 5 not 4 Some people will count 1, 2, 3, 4 and then tell me it's 4p, 5p because p starts from 2, it doesn't start from 1. So it's a 5p overlap. Now what if there is hybridization? Will the hybridization state change? Will it become another hybridization state for this iodine?
No.
No. Okay, it's still sp3, sp3. The hybridization state doesn't change. Right? Now, very simple example. If let's say I have methane, it is sp3 hybridized, correct? Even if I change carbon to silicon, or the rest is the same, it is still sp3 hybridized. Right? So, the same concept, I will make it brighter. Right? So, since both are sp3, then how are they different? For iodine, it involves what S and what P?
5S, 5P.
5S and 5P, correct. So even though they have the same hybridization state, the orbitals that are involved in the hybridization is not the same, right? You should know from your atomic structures that no matter which one you are comparing, whether this pair or this pair, right? These orbitals are always bigger than this, correct, as illustrated there, which means that the overlap is very, very diffused. Another way you can explain is by saying that, okay, for iodine, if let's say this is my nucleus, this is my nucleus, the electrons are further away from the nucleus, so the attraction is very, very weak. So it's very easy to broken, compared to fluorine, whereby these two are very, very close. So the attraction is stronger and the bond is harder to break, right? That's the first one. Next one is your bond polarity. So now if you were to look at the example, you have a HO bond and a HF bond, right? For a HO bond, you see that the partial positive and partial negative are relatively smaller than HF. Why is that so? It's because of the electronegativity difference, right? If you refer to the previous part, there's a practice for you, right? Whereby it asks you how the relative sizes of your delta plus and delta minus will change, right? So for this case, your delta plus and delta minus for HF is bigger. So like what I said last time, a bigger charge means the attraction will be stronger for opposite charges which are of bigger magnitude, right? So therefore for your HF, it is stronger than your OH bond. And next is your number of bonds. This one is very, very obvious. So a triple bond is stronger than a double bond than a single bond, right? So do you think a double bond is twice the strength of a single bond? Why?
Because the second bond is a pi bond, the first one is a sigma bond.
So the
Pi bond is weaker than the sigma bond, so
yes,
it's not
correct.
double.
Correct. Okay, so that's the answer. So for now, can you try the next example? Careful, there's a trap somewhere. Actually, you can make use of the bond energies in the data booklet, right? You might need a data booklet for B. FF is here. So I believe you are stuck at the second one, right?
The second one I don't know how to explain.
Is it by like showing shielding or something?
Hmm?
Shielding off.
You elaborate further. For second one, definitely cannot use the effectiveness of overlap, correct? Explanation, then how?
This one, I think I read in my notes that, like, because FF, like, the radius is very small, then, like, when they're very close, they will repel.
Yes, correct. Okay. So why is FF smaller than CL when it should be longer? The reason is because F is very, very small, correct? Now remember, how do you form covalent bond? The two electron clouds must come very, very close together, correct? So for FF, it's so small that when it comes so close together, there will be repulsion between the nucleus as well as the electron cloud, correct? So this repulsion actually pushes the two fluorines away so that it is in fact longer than your ClCl, or you can say it's weaker than your ClCl, right? Most schools teach this in group 7, right? You have learned group 7, right? Correct. Under periodicity.
Yeah, I think so.
Yeah, right. So this is the reason for why fluorine is stronger.
School haven't learned the periodic table yet.
I haven't learned yet. Okay. So next, the last one, OO versus CC. OO and CC are here. What could be the reason? If you do by elimination, the second one, which is bond polarity, you cannot use, right? And you also cannot use number of bonds. So most students will look at the first one, effectiveness of orbital overlap. But if you compare oxygen and carbon, they are in the same period, right? So there's not really that much of a difference in radius. So, which means you cannot use the first explanation. Then how? What's so different between a CC bond and an OO bond? Now if you were to draw the OO bond, right, you realize that apart from just the bond, what else does the oxygen have?
Just one electron.
There's lone pair, correct?
Yeah.
2 lone pairs here, and there's 2 lone pairs here. Now if you were to compare a CC bond, is there such a lone pair? No, so there must something, it has got to do with these lone pairs, correct? So what do you think is the reason to whereby this bond is in fact less than half the strength of this?
I call it VSC, no, what's it called? Electronic repulsion or something.
Yes, it has something got to do with repulsion once again, right? So take note, there's a lone pair here. So what can the lone pair do? The lone pair can?
Repel the...
Yes, they can repel each other, correct? So when they repel each other, this bond you don't really need that much of energy to break because there's already this repulsion force to help you. But for this, there's nothing there, right? So therefore, for OO bond, it is actually weaker than your CC bond, right? If you were to look at NN bond, it's also very, very weak, right? So, yes. So another trend that you should see is that if you were to compare CC bond with NN bond, CC bond is stronger. Now if you compare CC double bond with NN double bond, again CC double bond is stronger. Why? Because there is still lone pair. Okay, because N double bond and adopt this structure, so there's still lone pair. So there's still repulsion. Next, you were to look at NN triple bond, which is here, versus CC triple bond. Now which is stronger? It will be NN. Why? Because there's no longer lone pair. If you are comparing nitrogen gas, right, the structure is like that. There's no way for these two to repel each other because they are too far. They are not pointing towards each other, unlike this. Right? So there's actually a lot of whys if you were to study your bond energies, right? So next. Next part is on dot and cross diagrams. I believe you should be proficient in this by now, right? So I will just briefly go through the general steps in drawing. Do you have problems with drawing structures? For example, I give you a formula and then draw the dot and cross or Lewis diagram. Still okay, right? Later on we'll work on some practices and see, right? And hopefully you'll get wrong, right? Because when you get wrong, you will know your mistake and you will not commit it during your exams. So there's a few general shortcuts for oxygen. I believe your school should have taught you, right? For oxygen, it's either two single bonds, one single bond and a negative charge, a dative bond towards O, or a double bond, right? These are the four possibilities. And some exceptions to the octet rule. The first is your electron deficient molecules. So I already shown here your BeH2 being bonded to two ammonium molecules by forming two dative bonds, right? So such molecules forms what we call adducts, right? ADDUCTS, adducts. So you should have also seen this molecule from the previous example if I'm not wrong, right? I have a question whereby I ask you on the polymeric forms, right? So the second one is your expansion of your octet, or what we call hypervalency. So when the central atom has more than 8 valence electrons, and most commonly found elements that can have expanded octet are those which are here, okay, period 3 and below. Your school has taught you this as well. So for molecules here, which includes silicon, phosphorus, sulfur, chlorine, etc., they have low-lying vacant d orbitals, right? Vacant orbitals. So for example, take phosphorus as an example. So for phosphorus, I already taught you the hybridization state, right? The D2sp3, dsp3, etc. So for this case, if let's say phosphorus want to form bonds, of course it can form pH3 because there's 3 unpaired electrons, right? But you know that there are formulas for phosphorus with this px5, right? So in order to form 5 sigma bonds, what phosphorus has to do is that it has to excite one of the electrons to the vacant d orbitals and undergo hybridization, right? So this is expanded octacity or hypervalency, right? Next is odd number of electrons, okay, what we call radicals. So when the molecule has unpaired electron, this is also known as radicals. Examples are shown here. So usually in radicals, the more or the question is, will it be the more electronegative atom achieves octacity, or the less electronegative atom? The more, okay? Because more electronegative atoms attract electrons more towards themselves, while the less electronegative atom will attain odd number of electrons, right? So now radicals are very reactive. They react with one another so that they can pair up, and everything can achieve octacity, right? So if we were to look at radicals, one of them will have unpaired electrons, they will have 7 electrons. So in order to become stabilized, they will dimerize, right? So in order to check if a particular molecule is a radical or not, you just have to add up the total number of electrons and see whether it's an odd number. This is quite obvious. Because in order to achieve octet rule, it must be even. So I don't even have to draw you the structure. So for example, I can ask you, is Br5 a radical? So the answer is it a radical, Br5?
Yes.
Is it a radical? What do you think?
Yeah,
Why?
because BR
Hmm?
BR 2 forms that structure, then BR 4 will be there's 61 extra BR.
Hmm. Another way you can say is that they have 7 valence electrons. 5 times 7 is 35. There's no way to pair up all the electrons, correct?
Yeah.
So this is the fastest way. So if let's say I have an MCQ, those people who don't, actually is quite fundamental, correct? Quite logical. So for those who don't know, they'll start drawing, wasting their time, when you can tell the answer immediately, right? So just take note of this thing. Okay, next example, molecular structure. So can you draw the Lewis structure? Will be enough, right? For all of this. Just the Lewis structure. For the second one, N is the central atom, right? As a hint, N2O5 is symmetrical. minute, right? So how? Let's go through the first one, H2SO4, right? Look at the big picture if you are confused. H2SO4 is a acid, correct? So acid contains OH bond, right? In fact, for this you can call it an oxo acid because it contains hydrogen bonded to oxygen, right? So since you have this bond, and you should know that H2SO4 is a diprotic acid, right? It can be deprotonated twice. So it makes sense to think that it should contain two of this, right? So now based on the general steps written here, usually you will place atom of the lowest electronegativity. So for this case it will be sulfur, right? So now there will be an O, O, and OH which are joined together, and another OH which are joined together. So how do you think they are joined to sulfur? This bond must be a single bond, aforementioned, right? This satisfies the A, right? That's the only way to join this oxygen. What about the other two oxygens? What about the other two oxygens? Don't draw yet, huh? There's a few choices. So for this sulfur, it has 6 electrons. So we already used 1, 2. So there's 2 more, 3, 4, 5, 6. So is it right to draw it like that? What do you think? Oxygen got 6, right? So shouldn't it make it 8? This one also 8.
Double bond.
Why cannot be like that? It also work, one. Everything is octet. Oh, this one also can. Alternative answer, is it? But this works, right? Makes everything 8, correct? So why can we accept this? Oh, this is wrong. This is answer A. Answer B is what you have proposed, whereby you adopt the double bond. Right? So which one is correct? This one or this one? No idea? Okay, actually neither are wrong, but this is the more preferred answer for A levels, right? I've written down there if you were to look at the note, right? So if given a choice between expanding its octet or not, an atom will always expand its octet, right? So this is actually, I'm not saying this is wrong, I'm just saying that this is more preferred for A levels, right? So the key point is, if you can expand, yes, you will expand, right? So for this case, there's how many electrons around sulfur? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this is the more preferred structure, the expanded one, right? So this is the structure for H2SO4. And same thing, apart from H2SO4, if let's say I have another oxo acid, for example, H3PO4, right? How would you draw it? You should know that H3PO4, right, is contains H3PO4, right? H3PO4 should contain 3 OH bonds, right? So now you see the trend. Is it very cool?
No.
Okay.
It's sort of like a photo.
Okay. So for H3PO4, you have 3 OH bonds, right? So the same thing. P will be bonded to 3 OH, 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 and OH. And the last one is a double bond O, right? The pattern is always like that. No matter it's H3PO4, H something, right? In other words, H, X, Y, O, Z, right? The pattern is always like that. So just take note. So next, what if it's just SO4 2 minus? Then it's the same thing, correct? If let's say I have SO4 2 minus, look at B, right? This part, the B, which means that you should have 2 of these species, which means you will have one of this here and another of this there, and the rest is double bond still, right? This is just your H2SO4 but deprotonated, right? That's your H2SO4. So I believe you can easily convert to dot and cross, right? So the next one is N2O, right? Do you have structure for N2O? Okay, let's look at Nicholas' answer. This answer, right? So what's wrong with this answer? Is there anything wrong with the answer?
The middle end got like
5 bonds, okay? So remember to always obey your octet rule. This nitrogen got 5 bonds, right? So this structure is wrong. And like what I mentioned, N is in the center, so how are you going to join them together? How are you going to join them together? Actually, for easy structures like this, you can either do by trial and error or get to the answer straight away, right? So if let's say you do trial and error, 1 bond, 1 bond, correct? We'll just go with 1 1 2 2, then 1 3, etc. Right? Sometimes it's faster that way. So 1 1 definitely won't work, right? So now add another bond here. Does it work? It doesn't work because this O must either be A, B, C, or D, correct? But for this case, can it be A? It can't be because it's terminal. Can it be B? No, it can't be because there's no charge. So it's either C or D, right? So you can skip this straight away, the single bond. So you just consider dative bonds first, right? So now if let's say I have a dative bond, does it work? You can fill in the other electrons and see, right? So these 2 electrons must come from nitrogen, so this nitrogen must form another triple bond with this nitrogen in order to spend all its valence electrons, right? So now you have the structure of your N2O where everything achieves octet. And if let's say this doesn't work, then of course you can try the second scenario, right? Yeah. Next, same thing, N2O, right? Will this work? For this side, it looks like it will work, correct? Then for this side, what should it be?
Double bond, so
Double bond? Like that?
wait, no.
Does it work?
One dative, one bond.
Hmm?
One dative.
Yes. Very good. Right? Nobody say a single bond. Nobody say you cannot do like that. Correct? Why? The most easy example which shows this kind of bonding is actually your carbon monoxide. Right? Carbon monoxide looks like it's very simple to draw. Correct? But if we were to draw a dot and cross, what do you realize? This is actually one of the examples previously. Right? You realize that if, let's say, you draw it in this way, you realize that carbon actually has 5 electrons. Oxygen actually has 5 electrons as well, which doesn't make sense. So the last bond here is actually a dative bond. So that oxygen got 6 electrons, carbon got 4 electrons. So this bond is actually like that. Right, just that a dative bond is also a covalent bond, so people just draw it in the normal way. Right? In case you don't know carbon monoxide, so this is actually another scenario whereby you can make use of the dative bond. Okay? In other words, these two structures both are acceptable because there's no expansion or whatsoever and both achieve octacity. But obviously this one looks nicer than the answer. Right? Later on we'll see which one is the correct answer. Actually both are correct, just that they are resonance structures. Right? This is the N2O. Next, N2O5. Right? How do you draw N2O5? She has drawn one structure, right, which is like that. Very good, because I didn't manage to think of that structure. Right? No, it's actually the same. Sorry. Right? It's actually this structure, N2O5. Now this tells you one thing, right? Look at the general steps. The first step, right? From the molecular formula, some people will think they must place atom of lowest electronegativity in the center and the rest around it. For this, the central atom is O, oxygen. Right? Everything revolves around this oxygen. So it's actually not right if you strictly follow the first step. So that's why this example teaches you to be flexible, right? So Wen Yan drew this structure, but this structure is not correct yet, right? Why? Because of the terminal oxygen, correct? It's not balanced. So how?
Dative bond.
Dative bond, right? You can try these 4. Whenever there's oxygen, you think of these 4. Since I have a terminal oxygen, you cannot have A or B. So it's either C or D, right? So you can start off by trying dative bond. Does dative bond work? You must have 2 dative bonds, right? Which is like that. 2 dative bonds. Does it work? Yes, it works. Correct? Do you have to try double bond? Or do you think double bond will also work? Will double bond work? In other words, can you draw it this way? Can I? Cannot, right? Because nitrogen got 5 bonds. Then can you draw it this way?
I think can.
Can, right? So again, which one is the correct answer? Like that or like that? What do you think? Or both can? Oh, you are confused already.
Both can.
Yes, the answer is both can. Right? For this, there's not really a straightforward comparison. Right? So both can. So if you draw, either one is correct. Okay? Can, before, because you never disobey any rules. Right? So both can. That's your N2O5. Next is your MnO4 minus. Remember, just now we did SO4 2 minus. Now we did MnO4 minus. How should we draw this? Whenever you have a negative charge and oxygen, remember, usually the oxygen will acquire the negative charge, so it resembles B, right? So which means it must contain this bond. So it's quite obvious that Mn is the central atom, and Mn is a transition element, right? So it can have expanded octacity as well, which means you will adopt this structure, just like similar to your SO4 2 minus, right? So this is your MnO4 minus, and the last one is NO2. Okay, remember what we did just now, the last sentence, right? If the total number of electrons is odd, it will be a radical. So oxygen is from group 6. I have 2 of them, that means all must be paired. So I'm left with nitrogen, which is 5. So that means it must be a radical, right? I can forget about my conventional kind of bonding. There's ought to be a radical. And I ask myself, which atom will have the unpaired electron, nitrogen or oxygen? Nitrogen, because it's less electronegative. So before I do anything else, I just put a lone electron here, right? So now these 2 oxygen must be terminally placed. So which one will it be? A, B, C, D. It cannot be A, it cannot be B. So it's either C or D. Again, nitrogen contains, use dot now. Nitrogen contains electrons, right? So will we do this or will we do this? Can you do this? Cannot, right? Because nitrogen will have 9 electrons. So can you do this? Wait, just now, right here. Sorry, this one is wrong. What am I talking? This doesn't work, right? Because 1, 2, 3, 4, 5, 6 electrons. Only this will work, okay? My bad. This one doesn't work, What was I thinking? Okay, See, I also make mistakes, right? So it's a double bond and a dative bond, right, for this. So you can change your answer. Yeah. So for this case, this doesn't work, right? This doesn't work, then what else? Of course, 1 double bond, 1 dative bond, that's the last choice. You cannot have any other pattern already. So this will be the final choice. So this achieved octet structure, this also achieved octet structure with nitrogen containing 7 electrons. Right, this is the best that you can achieve. So your NO2 is a radical, right? So I hope you have learned something from these examples. So next, just very quickly, delocalization and resonance. So this part was only added to the new syllabus. So by now you should be familiarized with the bond line drawings. So for example, if let's say I have a carbonate, you should be able to draw the structure of your CO3 2 minus, right? Because the 2 minus will come from 2 times of B, right? So that's your CO3 2 minus. So now you might wonder, since I have 2 single bonds and 1 double bond, where the double bond lie? It can lie on either oxygen, correct? Which is shown by this structure. So which one is the more correct structure? Which one of these? Or are they all equivalent? In fact, all of them are equivalent, right? If you look at the bond lengths, all the CO bond lengths are the same, and all the CO bond strengths are the same. And the bond strength lies somewhere between your CO single bond and your CO double bond, right? So now scientists observe these phenomena, so they end up with this hypothesis by saying that, oh, electrons can actually delocalize in the system. So this means that, right, take note, this doesn't mean that the electrons will jump around, right? What I'm drawing here is just to help you illustrate how the electrons move, but in reality, electrons doesn't move. It's a hybrid resonance, what we call a resonance hybrid structure. It doesn't convert from one form to another. The real form is actually a mixture of these 3, right? So that's why for the bond strength and bond length, it's between a single bond and a double bond, right? So the arrow movement actually indicates the delocalization of electrons. So the blank is for delocalization, right? So these structures are known as resonance structures, and they show the charges in different places, indicating their delocalization. Common misconception is that students tend to treat the resonance structures as different entities, but they are actually just one entity, and they don't flip back and forth. So this is just like a unicorn, right? Some people say unicorn are the offsprings of horses and rhinos, but they don't flip between horse and rhino. Today horse, tomorrow rhino. No, it's always a unicorn, right? So this is something like unicorns, the concept. So it should be noted that delocalization of charges allows the charge to be more dispersed and stabilized, and this stabilization is more commonly known as your resonance stabilization, right? Have you done the chapter of A rings yet? Have you? A rings? Done already, right? So you know that benzene has also resonance stabilization, right? It's due to the same principle. So here are some examples. How many structures can you draw for the following species? The first one is your SEN minus, right? They are connected in the same way. S is connected to C, connected to N. Right, so it's just like that. It's just how you want to place the bonds. Right, I want to see how creative you can get. There's a minus charge, I think. So do you manage to draw SEN? You should have at least one structure by now, huh? I'll go through first. So this is the first structure which is possible, and the negative charge lies on sulfur. Okay? Sometimes students might argue, why is a negative charge on sulfur? It is not the most electronegative element, right? But my answer is you don't have to be a most electronegative element, right? All these are just general rules. They are not laws. Laws you cannot break the law, but you can break a rule, right? So this everything achieves octicity, so no problem with that. Another one is this structure, whereby the negative charge lies on nitrogen. It is also acceptable, right? Everything also achieves octet structure, right? So if you are asking which of these answers should I draw during exam, the answer is either one. You never break any rule, but this will be the more preferred one because the negative charge lies on the more electronegative atom, right? In fact, you can convert this to this just by using two resonance arrows. This shows the delocalization, right? So what about the next one? N3 minus. There's only one way to connect them, right? just for information, I think some schools teach this way, right? SCN and then put a negative charge outside, correct? Correct. Like that it also work, right? If you draw it like that, the thing is that now you don't know the negative charge is on which one, which means that both of these can become acceptable because it's quite vague, right? Just take note. Okay, so like the previous one, it's also a 1, 3, right? So how are they connected? 1, 2, 3, like that. For this one it'll be 1, 2, 3, 4, 5, negative bond. This will be 1, 2, 3, 4, 5, and the next one here comes from somewhere else. So a negative charge lies on this nitrogen, right? So you see that this structure is actually similar to this structure. So same thing, these can delocalize and you can represent this structure this way. Right, it's just like this. Okay? So I hope you gain some knowledge from this example. Next one. No longer drawing, right? Now it's about structure of your molecules. So since covalent bonds are directional, remember what I talked about, ionic bonds are non-directional, right? If there's a cation here, if there's an anion here, they can attract each other. If the anion shift here, they can also attract each other because the force is around you, it's like gravity, right? But for covalent bonds, they are directional. Sigma bond and pi bonds have specific directions, and the molecule that they form also have distinctive shape and bond angle, which can be described by the valence shell electron pair repulsion theory, VSEPR theory, right? So electron pairs in valence shell of central atom of molecule tend to move as far apart from each other as possible in the 3D space to minimize repulsion. So the aim is to minimize repulsion, right? So that they become energetically more stable. So such a phenomenon causes bonds to space out and adopt different shapes and bond angles, right? So now the extent of repulsion, I believe your school has taught you, right? Lone pair is greater than lone pair, bond pair is greater than bond pair, right? But for me, I don't teach these three only. There's the last one which I want you to take note is your lone electron. Lone electron anything, lone electron, lone electron, bond pair, etc. Right? Now why do I mention lone electron? Let's say you have this. This is the one that we drew on just now, right? Now I ask you, what's the bond angle? How do you calculate? Or if you, let's say you were to compare this with a typical kind of structure which is like that. Okay, this has a lone pair, correct? So this is going to adopt a band shape. And then you will say that, okay, so since it's a band shape, that means the angle is maybe, sorry, this one, ammonia, let's say, 3. So the angle is going to be 107 degrees. Then what about this? What's the bond angle? Are you going to say that, okay, since it's bent, so it's going to be maybe, 125 degrees or what? You've never seen such a problem before yet, right? Or seen already? If you haven't seen it, that means soon you'll see it, right? Usually students will stumble at this because they don't know what's the bond angle. Now if you think of it, if you were to compare a lone electron with a lone pair with a bond pair, right? All of these involve 2 electrons, while only these involve 1 electron. So in fact, this repulsion is actually even weaker than either one, right? So in fact, this bond angle is much greater than 120, right? If I'm not wrong, it should be 130 something, right? But the concept is still the same because I only have 1 electron, so the repulsion is less, right? So therefore, I place it here with the lowest priority, right? So the actual bond angle you won't be able to predict, but at least you will be able to predict their relative bond angles, right? So now lone pair exert greater repulsion as they are closer to a nucleus than bond pairs, right? Since they are only held by one nuclei. Most schools just teach lone pair closer to nucleus, so experience less repulsion. But students don't know why they are closer, right? So I've given you these two examples, ammonia versus your ammonium, right? So if you were to look at ammonia and ammonium, for ammonia, the lone pair is only held by your nitrogen. But once it bonds to hydrogen, the electron will be further away from nitrogen because it's now somewhere between hydrogen and nitrogen, right? Does it make sense? So it makes sense to think that if let's say I have a lone pair, you exert a greater repulsion than a typical bond pair, right? So that's the reason. So in order to predict the shape of molecules, these are the general steps that you must follow. First is draw the Lewis structure, which is what we did just now. And then you count the total number of electron regions, right? What do I mean by electron regions? Let's say, for example, just now, H2SO4, right? The total number of electron regions around this sulfur will be 1, 2, 3, and 4, right? This is what we call electron region. Or if let's say you have ammonia, right? The number of electron regions will be 1, 2, 3, and 4, right? So once you count the total number of electron regions, you recall the basic geometry, right? I've listed in the table here. So if let's say you have electron region 2, right, the basic geometry will be the leftmost one, which is linear, followed by trigonal pyramidal, etc. Right? These are the what we call the basic geometries. Okay? So after you recall the basic geometries, you will modify the geometry based on a number of lone pairs. So if you have one lone pair, so if you have 0 lone pair, it will be this. If you have 1 lone pair, it will be here, 2 lone pair, 3 lone pair. Right? So finish, that's all, right? And just take note, geometry is based on bond pairs, not lone pairs, because you cannot see electrons, but you can see the physical bonds there being present, right? So for example, H2SO4, around this sulfur, I have 4 electron region, so I look at 4. Do I have any lone pair around this sulfur? No. So it will be tetrahedral, 109.5. For ammonia, there's 1, 2, 3, 4 electron region, 1 lone pair, so I look at here, it's trigonal pyramidal, it will be 107 degrees, right? All these bond angles you can actually derive yourself, right? So now the question is this: if let's say I have this structure, extension, see whether you can do it or not, right? Versus this, okay? Compare their bond angle. Which one is larger? Which one is smaller? Or are they the same? X is just atom, there's no lone pair or what?
That's smaller.
Yeah, smaller. Why is it smaller? What's the basic shape first for these two? Basic geometry. Tetrahedral. Okay, so tetrahedral. Do they have lone pair? No. No lone pair, right? So both are tetrahedral. So why is this smaller?
It's bigger.
Why is this bigger?
Because the electron is further away, because O is more electronegative. If you ignore, that's not carbon. But that was carbon.
So why? Actually, sometimes you have to be flexible and think out of the box, right? Don't always keep this in mind. So both are tetrahedral, right? I have Y, Y, Y. These are Y, 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 Y. There's nothing got to do with electronegativity, right?
Yeah.
Now, you have learned that a double bond is electron rich, right? So that gives you a hint. So if you see electron rich, what will happen? Greater repulsion. Yes, very good. So there will actually be greater repulsion. Makes sense, right? Than a single bond. So if there's greater repulsion, this bond angle ought to be smaller than 109.5. Right? Well, for this is 109.5. Okay, there's nothing got to do with electronegativity. So of course there are other interesting examples, but I'll just talk about this, right? So this is how you can predict the shape of molecules. Always apply these steps, right? If you want to get it correct. So what if I have 7? What will happen? If let's say I have a formula X, Y, 7, what is the shape? and let's say there's no lone pair. I teach until 6 doesn't mean I have to ask until 6, right? And it's not possible for me to list out everything. What's the shape? X, Y7. Example will be IF7 for info, right? So if let's say I have X, Y7, X in the center, correct? The Y will be spread out accordingly. So it's actually gonna be spread out more or less this shape, right? This is a pentagon, right? And top and bottom, right? So how do you describe this shape? Look at the previous one. If let's say you have 3, okay, in the axial position it's called trigonal bipyramidal, right? If let's say you have 4, although it's tempted to call it a square bipyramidal, but its actual name is octahedral. So if it has 5, it will be called pentagonal bipyramidal. Correct? It's just derived from the top. Correct? And if let's say I were to change this Y, one of the axial Y, to a lone pair, then how do I describe the shape? Look at the one with 6 and 1 lone pair, right? It's called a square pyramidal. For this, it will be called a pentagonal pyramidal. That's all. Correct? It's all derived from the top. And if let's say I have another lone pair which is here, it will be called a
pentagonal planar.
Yes, correct. It's all derived from the top. Correct. Doesn't mean I teach 1 plus 1, you don't know what's 2 plus 2. It's all derived. The concept is the same. Right? Yeah. So next, some factors affecting bond angle. Other than number of bonds and lone pairs, which we saw just now, there are some other factors. First is your electronegativity of your central or terminal atom. So if you were to look at H2O and H2F, right? If you were to look at the bond pair, I've purposely drawn the 2 bond pair closer to F, further away from H. This is because F is more electronegative. So whenever you're confused, you can always draw diagrams like this to help you understand. So for this case, the second one, the bond pairs are actually further away from each other. Right? So the repulsion is smaller. So it's actually, there's a blank there, right? So terminal atoms more electronegative than central atom. Right? We will attract electrons towards themselves, so the bond angle is actually smaller. Right? This is quite, you can tell visually, right? Next is your size of terminal atoms. So if you were to look at Pi3 versus PCl3, I is bigger, although I is less electronegative than Cl. Right? So since I is bigger, it's going to exert greater repulsion, so the bond angle is greater. Right? So yeah, experiences of steric repulsion. Right? So now the general rule of thumb, now the question is, so when do I use electronegativity? When do I use size? Correct? Because the first one talks about electronegativity, the second one talks about size. So the general rule of thumb is that if let's say you are comparing atoms of the same period, you use electronegativity. Right? Now if you are comparing atoms of the same group, you use size. Right? This is a dominating factor for period, this is a dominating factor for size. Dominating factor for group. So if you were to look at hydrogen and fluorine, you can treat them as the same group. Same period, right? So you use electronegativity. Right? So next part is your molecule polarity. So recall that we talked about bond polarity previously. Now we'll talk about molecule polarity, right? If you were to refer to the first part, we talk about how to draw the dipole moments, etc., right, for the bond. So now we'll look at the molecule, right? So polar or not, we can actually split them into a few categories. First is your polar, second one is your non-polar, basically just two, right? So in order to look at whether they are polar or not, you have to focus on polarity of the sum of all the individual bonds, right? So in order to predict, you have to, same thing, follow these 4 steps, right? You must follow. First is you must use VSEPR theory to predict geometry, right? If let's say I throw you a molecule and ask you whether it's polar or not, then sorry, you have to follow this step first to obtain the shape, followed by these steps to obtain the polarity, right? So after the geometry, you draw a dipole moment arrow on the polar bonds, and if there is a net dipole, which means that they don't cancel out, you'll be polar. If there's no net dipole, you'll be polar. Okay? If there's no net dipole, you'll be non-polar. If there's net dipole, you'll be polar, right? So the second, in order to check whether a molecule is polar or not, you can use the test which is stated there, right? So if let's say you have a liquid containing polar molecules, they can actually be deflected by a charge rod if you bring it near to the stream. I believe you can do it for water as well, right? Because water is polar. And such phenomenon does not occur for non-polar molecules, right? So if you look at example 7, can you tell me which of the molecules are polar and which are not? And by the way, CH bonds are non-polar, right? We regard them as non-polar, right? Because remember, first part, we talk about which bonds are polar, which bonds are not, right? So CH bonds, because their electronegativity difference is very, very low, we regard them as non-polar. Okay? So now, which of the following molecules are polar? Just tick or circle or something, right? Be careful, sometimes examiners can be nasty, right? They draw in a way whereby it doesn't depict its real geometry, right? And examiners may not draw lone pairs as well. I'm gonna go through the first one first, so to start you off. So first one, I've CF2H2. Remember, even if I draw it like that, it look like as if you can skip your VSEPR theory, but no, right? If you skip your VSEPR theory, that means you have fallen into a trap. This is not the actual structure, right? So if you were to look at this, same thing, obtain the geometry first. The structure is drawn for you, so you don't have to draw. Count the total number of electron regions, that's 4, right? So its shape, there's no lone pair, so its shape is tetrahedral, right? So now you can redraw the structure in a tetrahedral fashion. Right. Next, draw a dipole moment arrow on all the polar bonds. So your CF bond is polar, this CF bond is polar, CH is not polar. Not saying not polar, non-polar, right? So do they cancel out? They don't, right? There's actually a net dipole moment here towards this direction. Sometimes students are confused with net dipole moment. This is just like forces. Both of you don't take physics, right? Correct. So how do you explain this? Just imagine you have a box in the center. A person is pulling here, a person is pulling here, and the other two is not putting any strength. Correct? So will this box move? Yes. If it moves, that means there is a net dipole. If it doesn't move, there's no net dipole. This is the easiest way I can explain. Right? So for the first example, yes, it is polar. Right? Now for the second case, same thing. Use VSEPR theory. Count the total number of electron regions. But for this, take note, I never draw all the electrons yet. Xenon is from group 8. I've only drawn 4 electrons. So there's lone pair on xenon, right? Lone pair. So same thing, apply VSEPR theory. Total number of electron regions, I have 1, 2, 3, 4, 5, 6. 6, and I have 2 lone pairs, so it's gonna adopt the square planar geometry, right? Which means it's planar lah, right? So since it's planar, I have hydrogen here, fluorine here, fluorine here. The dipole moment of the bond is like that. So if you have a box here, pull it in vertically opposite directions with the same strength, it's not gonna move, right? So since it's not gonna move, that means it's non-polar, right? Next, is this the only way to draw XeH2F2? You have learned isomerism, right? What do you think? Is there another way to draw it? Is there another way to draw this? There's an isomer, correct? How do you draw the other isomer? It is like that. Do you see the difference between this and that? So how do you name this isomer? Trans, then this is the cis, correct? Because they are pointing towards the same direction. For this is pointing towards the opposite direction, right? So now if let's say I have the trans isomer, will it be polar? Sorry, if I have the cis isomer, will it be polar? The trans one is not polar, correct? Because it cancels out. For the cis, yes, it will be polar. Because now there's nothing which cancels this out. There will be a net dipole towards this direction, right? In other words, the isomerism also matters if you want to consider polarity or not. Okay? Same thing, I can modify this question, right? And tell you that XeH2F2 have PD forces. Draw the structure of this. So if you draw this, it's wrong. Okay? So there's actually a lot of thought process behind it, right? So just look at the big picture. Then for next one, SF4. I think SF4 is easier, correct? How do you draw SF4? Same thing, you have to draw the lone pair, correct? So what shape is it? Seesaw, right? So do they cancel out? The two vertically opposite fluorines will cancel out, right? But the bottom two will not cancel out, so it's also polar. Right? And the next alkane, it is obviously non-polar. This long chain alkane, because everything is CH, so you don't even have to count. Then the next one, will it be polar? The squarish thing, is it polar? So if you were to draw the dipole moment arrows, it will be towards this O and towards this O, right? So they will cancel out lah. You can consider this O first. This O, there will be a net dipole towards this direction. For this one, there will be a net dipole towards this direction. So these two vertically opposite, they will cancel out. Right? Now geometry comes into play. We have learned this in primary school, right? So this one, the 6-member ring, is also non-polar because they also cancel out, right? And for this alkane, it is also non-polar because there's no polar atoms, right? And then for the last one, it's quite obvious that it's polar, right? You know why it's polar? You know why the last one is polar? There's a net dipole towards this direction for the O, right? What about the N? There will be one here, there will be one here. But the strength is not the same. So you'll never cancel out. Right? This is the same as, if let's say I have SCN, let's see. Right? Just now we talked about SCN, right? So for SCN, this bond is polarized towards S, this bond is polarized towards N. Do you mean that they will cancel out? No. Right? Because remember the practice we did earlier. although they might point to different directions, the length is different because the electronegativity difference is different, right? Which means this one should be longer than this. So there's going to be a net dipole moment. So if there's a net dipole moment, it's going to be polar, right? So that's why I teach this part first. Right, good. Next is intramolecular bonding. Okay, which are those intermediate bonds. So now this diagram is just for you, this graph is just for you to appreciate. You can see the percentage is plotted, percentage ionic character against the electronegativity difference, right? You don't have to see what that means, so you just look at the second part first, right? The other page, right? So ionic bond with covalent character. So cations can attract and distort electron clouds of anions. Electron density is drawn into region between the two nuclei, resulting in partial sharing of electrons, giving it some covalent character. So if you were to refer it to the previous diagram, it actually represents this one, the second one, right? Ionic bond with covalent character. Right. So because one atom is more electronegative, it actually distorts the electron cloud towards itself. So that there's some kind of partial sharing of electrons, right? So we call this kind ionic with covalent character. So the extent of polarization depends on the charge density of cation. Small cations have high charge density and polarizing power. So if you take Na plus versus K plus, Na plus is smaller, right? So it's gonna distort the electron cloud greater. Does it make sense? Okay, so small cations have high charge density, the blank is high. So next one, charge. Highly charged cations have higher charge density and polarizing power. Right? So if you were to compare this with this, and this is the electron cloud of your anion. For this, the positive charge is spread over a smaller volume. For this is a larger volume, so this is more concentrated, right? So you will distort this electron cloud more. While for this, the attraction is not so strong, so the polarization is weaker, right? So since this is stronger, there's more sharing of electrons, it has greater covalent character, right? Same goes for your charge, I won't draw for charge, right? Next one is your polarizability of your anion. Right, just now we talked about cation, now we talk about anion. So for the same cation, right? If let's say I have a highly charged cation, if I have a highly charged anion, they will have more electrons, which are less strongly attracted and hence more polarizable, right? Which means if I compare this with a negative charge and this with a 2 minus, right? The attraction for this will be stronger. Right, so these will be more polarized, these will be less polarized. So since it's more polarized, you have greater covalent character, right? Size also matters, right? If I compare one with smaller size and one with larger size, the larger one is very obvious that it's more easily polarizable, right? So for the one with larger size, it will have more covalent character, right? This is for ionic bond with covalent character. Next is covalent bond with ionic character, right? And by the way, this is for you to circle which one wins over, right? For the first one, it will be sodium plus because it's smaller, right? For the second one, it will be Ca2 plus because it has greater charge. For the bottom one, S2 minus have greater charge, and for the size wise, NO3 minus has a greater charge, greater size, right? Next one, when there's an electronegativity difference in the bond becomes polar. And in a polar bond, one atom acquires a partial positive charge, the other one partial negative charge. And with this separation, the bond exhibits some ionic attraction for each other, right? Because ionic attraction is between positive and negative. So if you have a partial positive and you have a partial negative, they can attract each other as well. Right? So the greater the charge, the greater the attraction. And this depends on your electronegativity difference, which I've gone through previously. Right? I've already shown you in example 1 how electronegativity difference affects your relative sizes of your total plus and minus. right? So example 8, discuss how covalent character in ionic compounds affect their melting points. So if let's say I have an ionic compound, pure ionic compound, let's say hypothetically, right, we assume this is purely ionic. Another one whereby this exhibits some covalent character, right? Which one will have higher melting point?
Oh, covalent character.
You sure? The answer is the one which is purely ionic, right? We have higher melting point, right? But why for this it has lower melting point? Try to make a guess. Why is this so?
Because if it's covalent character, then it is a partial charge, not a full charge.
Now, if let's say I give you a covalent compound, let's say CO2 got covalent bonds, right? Why does CO2 sublime at such a low temperature while, let's say, NaCl melts at such a high temperature? It's because if let's say you have covalent character, what you are breaking is actually the intermolecular forces, correct? The intermolecular forces is definitely much weaker than ionic bonds. So for example, for this case, you have 100% ionic bonds present. For this is maybe 90% plus 10% of intermolecular forces. So very obviously this is harder to break than this, correct? So that's why atoms which are species which are purely ionic have higher melting point, right? This is just an analogy to explain to you, right? That's intramolecular forces. Next is intermolecular forces, right? So for intermolecular forces, they are electrostatic in nature and they exist between molecules, right? In other words, from this part onwards, we'll be focusing on molecules, right? Not ionic bonds or whatsoever, right? So the type and strength of intermolecular force affects the physical properties of simple molecules, right? Those with stronger IMF will have a higher boiling point, right? You should know by now. So another key point to take note is that during physical processes like melting, boiling, dissolving, whatsoever, IMF is affected, but covalent bond does not change. You don't break the covalent bond, right? If you are talking about diamond graphite, that is not intermolecular force really. That one will be solid state, right? Which we'll be talking about later. So in order to predict a type of IMF, right, same thing, you have to follow this rule. All molecules will have ID, right? If let's say it's polar, you will have PD. If it has OH, NH, and HF bonds, you will have hydrogen bonds. In other words, if let's say for water, right, what IMF exists in water? People will tell me hydrogen bond, which is wrong. All three types exist, just that HB is the predominant one, right? Just take note. When we talk about hydrogen bond for water, it's actually very wrong to say that hydrogen bond exists in water, because all three forces exist. It's either all three, or these two, or just this. There's no such thing as purely hydrogen bond or purely PD, no such thing, right? So there are some types of intermolecular forces. So the first type, you have a sodium surrounded by water molecules, correct? So this kind we call it a ion dipole, right? Then the second type, you have a methanol and a H2O. It's a hydrogen bond, right? And for the last one, for the third one, you have a methanol and a chloroform, CHCl3. What kind of interaction is it? Cannot be hydrogen bond, correct? It must be PD, because both are polar. And a lot of students, I find they get confused, because if let's say you mix one liquid with another liquid, then they don't know the intermolecular force really. That's why I don't specifically say, oh, between chlorine and chlorine, between water and water. I'll tend to mix between water and ammonia, between water and chlorine, whatsoever, right? So that you can see more examples, right? Learn more examples. So the last one, you have an octane and another hexane. Both are nonpolar, correct? So it must be ID-ID, right? So these are different kind of intermolecular forces. And just for information, the relative strength of your intermolecular force, you see that hydrogen bond is about 10 to 40 kJ per mole. Dipole is 5 to 25. Dispersion is 0.05 to 40, right? The other kinds which I never asked you to fill in is just for information, right? You don't have to know. Only those which you fill in you have to know, right? So if you were to compare a typical hydrogen bond with a covalent bond, you can see the hydrogen bond is actually quite strong, right? It's actually a third of your covalent bond strength, right? So let's talk about the first kind of force, van der Waals forces, ID-ID interaction. So I won't go through because I believe this explanation everybody also can come up with, but those who can write this explanation may not actually know what is happening, right? So now let's say you have a molecule, right? Hexane, for example. At one instant, all the electrons are evenly distributed. This is the neighbor, are evenly distributed, so there's not going to be any attraction. You know that electrons are very, very naughty, correct? You cannot keep them at one place. So at one moment, the next moment, more electrons may get to here, less electrons may get to there. Right? So there's more electron here, less electron here. So what happens here? Since there's more electrons, there will be a partial negative charge, and there's going to be a partial positive charge, right? Conservation of charge. So since there's more charge here, what will happen to the neighbor? If I'm negative, you will repel the electrons from here, correct? So this negative charge actually repels the electron from here, such that it also adopts the same electron shape, I will call it, right? So once your neighbor adopts this shape, what happens is that you have a partial negative, you have a partial positive. There's ought to be some kind of attraction between them, right? Just now, when nothing happened, I call it t equals to 0 second. Now it's t equals to 1 second. This is the timeline, right? Next moment, right, the electrons may start to behave well once again, and it might go back, right? So once it go back, everything becomes evenly distributed again. So when everything is evenly distributed, it's not going to have any effect on its neighbor once again. So this attractive force is actually gone. So this is t equals to 2 seconds. And of course, this process can repeat itself, right? It is ongoing. So that's why sometimes the force is there, sometimes the force is not there. And that's why your ID-ID forces are the weakest, because it's temporary only. It's due to the temporary fluctuation, right? In fact, what I've explained here is just the easier form of what is stated here, right? So therefore, ID-ID forces are generally weak, right? The blank is for weak and easy to break, precisely because they are temporary, right? So some factors affecting strength of ID-ID forces, easier to understand this way, right? So ID-ID forces, the number of electrons or electron cloud size. If let's say you have a greater electron cloud size, it's easier for the electrons to get unevenly distributed, correct? So the ID-ID forces will be stronger. So here are the examples for the noble gas, right? You can tell from the boiling point, right? Krypton is the largest, it has the highest boiling point. Next is surface area. For molecules with the same number of electrons, branching introduces smaller surface area, right? So smaller surface area means smaller area to act. So if you were to compare this versus this, right? For this, you can attract here, 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 anywhere. But for this, there's limited surface area for you to act upon. So since for this case, there's more surface area for you to act upon, there's more ID-ID forces. Sorry, ID-ID, I'll call it forces to break. So therefore, you need more energy input to break these kind of molecules compared to this, right? The example is also shown there. So since ID-ID forces arises due to fluctuations in electron density and that all molecules contain electrons, right? You should know. Therefore, it exists in all molecules as well. As long as you you have electrons, ID will be there. So it doesn't have to be for polar atoms, polar molecules only, right? So ID also exists in water and other polar molecules. So next is your PD. So remember just now we talked about temporary fluctuation, right? Next, let's say you have a molecule, right? I draw it in a nicer way. Let's say you have a molecule, right? And the molecule is polar. If it's polar, there's gonna be a place whereby there's a permanent delta minus, and there's gonna be a place with permanent delta plus, right? So when you put molecules like this together, what you're gonna see is that there's gonna be attraction, and this attraction is permanent as well, compared to just now, which is only temporary, right? So since it's permanent, therefore PD forces are generally stronger than your ID forces, right? So they are stronger. The blank is for stronger, okay? So factors affecting strength of PD forces is your molecular dipole moment, like what I mentioned, right? Previously during the first page. This partial plus and partial minus can be modified depending on what atoms you are using, whether they are more electronegative or less electronegative. So in fact, different atoms will have different relative sizes. So of course, if you have one which is more polar, which is like that, the attractive force is going to be even stronger, right? So this is how it affects it. And since PD forces arises due to dipole moments of molecules, therefore only polar molecules have PD attractions, right? So lastly is your hydrogen bonding. The NHO, H and FH bonds are very polar due to the highly electronegative NOF atoms. So electron density is withdrawn from H, leaving H with a significant delta plus, right? So this time we are talking about XH bonds, right? Due to X high electronegativity, this bond pair is very, very close to X. So this delta plus is very, very big, right? So what you do is that if let's say you have another HX, you can attract the lone pair, right? And we define this kind of interaction as a hydrogen bond, basically, right? So I've already shown the HF interacting with two water molecules, how they can interact. Okay? So HF is the strongest kind, it's almost a third of the weakest kind of covalent bond, right? So some factors affecting strength of hydrogen bonding. First is your dipole moment via HX bond. So I've shown here your HF, HO and HN bond. You can see the dipole moment arrow getting smaller and smaller. So for the same Y, right, your HF bond is going to be stronger. Because your H, if you want to draw the partial positive, it's really drawn there, yeah. The partial positive is the greatest, right? Secondly is the ease of termination of the lone pair. Greater ease means stronger hydrogen bond. So if let's say your X is the same, just the one which is donating lone pair is different, you will see that nitrogen, which is the least electronegative, right, will donate the electrons more readily to H, so the hydrogen bond is stronger as well. And generally speaking, for the same X and Y, just take note that HF is stronger than HO than NH, right? And lastly is the number of hydrogen bonds formed and also the extensiveness. So the greater number of lone pairs and hydrogen atoms means more extensive, right? And also means stronger hydrogen bonding. So if you were to compare this versus this, right? So which hydrogen bond is stronger, between water or between ammonia? So you see for oxygen there's two lone pair, one molecule and two hydrogen, right? For this there's one lone pair and three hydrogen, which means maximum these can form. If you just look at one molecule, it will form one. For this it will be 2 times the chance. So this is going to be more extensive, right? So since this is more extensive, that means you require more energy to break. That's why this in room temperature is water, liquid, or this ammonia is a gas, right? Unless you dissolve it. So example 9. Let me try example 9. L3? Can I write L3? You must tell me between this and water what interaction is there. So my suggestion is just to do up a table, right? So here is this molecule. You have water present, correct? H2O. You have Na plus. You also have Cl minus. So for this, put the same thing, this thing, Na plus, Cl minus. So between this and this, one interaction, this and this, etc. Of course, you don't have to do this now, right? Because it's the same. Sorry. Not diagonal. Cancel one side. Because these two can interact. Because this is the same as this one, right? So between these two molecules, like what I mentioned, you should always have ID-ID, correct? So they are polar, it will be PD-PD. Hydrogen bond can? Cannot. What about H2O and this? Same thing, you can have ID-ID, you can have PD-PD. Can you have hydrogen bonds? Can. This one can hydrogen bond to this, right? Because remember, there's a lone pair, right? Take note, hydrogen bond doesn't mean H2O and H2O or HN or HF, right? This lone pair can come from anywhere, need not be another oxygen, right? But the interaction of a lone pair with a hydrogen is called a hydrogen bond. Right? Some students think that, oh, this one must be O, must be F, must be N. No, it can just be a lone pair, right? So there can be ID-ID, PD-PD, and hydrogen bond, right? Next, what about these two? Sodium plus and this species. There can be ion dipole, right? How is it going to be orientated, right? You have this, draw here. You have the Na plus here, right? The plus is going to interact with the lone pair on O. This is going to be a lot around this ion dipole. What about Cl minus? Can you interact with this in the same way? Cannot, because this is negative, this is also negative, right? there can be interaction, but I don't want to confuse you, so just assume that there's no interaction, right? Next, between water and water, this is quite obvious. There's going to be ID, PD, and hydrogen bond, right? Na plus and H2O, there's going to be ion dipole. Between Cl minus and H2O, there's going to be ion dipole as well, right? This is the same as solvation, right? Whereby you solvate your NaCl in water. Next is your Na plus and Na plus. Obviously, there's no interaction, right? Like charges repel what? For these two? Between Na plus and Cl minus. In order not to confuse you, you don't have to think about it, right? Otherwise it gets too complicated. So the main part is just this, right? You have to know all of this, right? So next, some phenomena observed by your hydrogen due to your hydrogen bonding is okay. This one will be uploaded, right? So you can view it. So first is your intermolecular hydrogen bond versus your intramolecular hydrogen bond. So due to the proximity in 2-nitrophenol, intramolecular hydrogen bond may form between the nitro and hydroxyl group, right? Between OH and NO2. So there will be less sites available for intermolecular hydrogen bond. Thus, intermolecular hydrogen bond is less extensive compared to your 4-nitrophenol. This is the classic example every school will give, right? So less energy is required to overcome the forces between 2-nitrophenol. Thus, it has a lower boiling point, right? So also due to intermolecular hydrogen bond, less sites are available for hydrogen bond water molecules. Therefore, 2-nitrophenol is less soluble as well, right? So hydrogen bond affects both your solubility and your boiling point. And next is the anomaly in melting and boiling point of hydrides. So if we were to look at hydrides, H2O and H3 have higher boiling points than the rest, right? The reason is also due to your hydrogen bond present in them, which is harder to break, right? Dimerization of your carboxylic acids. Molar mass of your carboxylic acids in the vapor phase and in nonpolar solvents is found to double, right? This is due to carboxylic acid existing as a dimer, so in aqueous solution, no dimerization occurs as more favorable hydrogen bond is formed with water instead, right? Why the formation of hydrogen bond with water is more favorable? Precisely because one of these, right, can form how many hydrogen bonds with water? There's one lone pair here, one lone pair here. There's lone pair here, there's lone pair here, there's hydrogen here. Compared to this, whereby it can only form with one other of its kind, right? So it's energetically more favorable to form with water. So next, you all are bio students, right? So you should know the complementary base pairing, ATGC, right? Or in RNA, uracil, right? So these are base pairing, complementary base pairing, which gives the stability of your DNA double helix, right? Or your RNA double helix. RNA also can have double helix, right? Okay, good. So example 10, hydrogen bonding. In water, with the presence of acid, a few HXOY structures can exist. So can you draw the structures of this? Maybe I start off the first one, so you'll know what I'm asking. So remember, for this case I'm asking about hydrogen bonding, right? You have water and you have acid, right? So H2O2, you know that acid contributes H+, right? So if I have H5O2, how is it formed? I have one water molecule will have one oxygen, correct? The oxygen can only come from water. This is the thought process. Oxygen can only come from water. So since there's two oxygen, I should have two water molecules, right? So since I have two water molecules and I have acid, I add these three up, just nice I have H5O2, right? By the way, I forget all the charges, so can you just put a plus charge for the first one? Right, so the structure of this is actually just O, H, H. Right, these can interact with H plus, correct? And this H2 has to interact with this entity. So how does it interact? It can interact with either hydrogen, right? So there can be another one which interacts with H. Either this, or this, doesn't matter. That's right. Yeah, correct. Right. Another way you can do this question is like that, right? So in water, H2O plus exists. You have learned this in acid base, correct? The structure of H2O plus is like that. Right. So the other water can interact with either hydrogen. Same lah. Right. Remember, for hydrogen bonding, always label the partial positive and negative charges, as well as label the bond, right, as hydrogen bond. If not, you draw dotted line, the examiner don't know what you're drawing, right? Okay, the rest you can try at home. So I'll briefly go through the solid state again. Here I think there's not much to copy, right? Because this part, O level, everybody learned before, right? Mostly. So I just highlight the important parts since you have learned it in O levels already. So solid state chemistry is about study of materials in the solid phase, right? So in solid phase, compounds pack themselves in the most efficient manner, and this gives rise to different type of lattice structures. Solid state is always about packing, it's no longer about polarity whatsoever, right? So there can be a few lattice structures, I've already stated there. And what are the lattice particles? Lattice particles means, remember when you ever have a lattice, right? There will be particles at the corner or at some place, correct? So these are known as lattice particles, right? So take note for simple molecular lattice, right? Is either atoms or molecules. Atoms means your noble gas lah. Atoms can be, molecules can be your CO2, can be your iodine, right? And lastly is your hydrogen bonded lattice. Lattice particles are your HX molecules. And the different kind of lattice forces already stated here. Basically this part is just a summary of everything that's below here, right? So first, your giant ionic lattice. The lattice energy can be calculated using the formula over there, right? So just for information, crystal lattice structure, there can be different kind of lattice structures. The first kind is your face center cubic. You don't have to know what is that because I already put FYI, right? The second kind is your body center cubic. I put it here so that you don't get confused, right? You have to know the one for NaCl, but not for CaCl. If you were to compare NaCl and CaCl, you're going to see some differences in their structure, correct? So this is just to tell you, or don't get confused or don't ask, how come it's like that? Okay, because different structures can adopt different, different species can adopt different structures, right? So properties, high melting point, boiling point, because large amount of energy is required to overcome the electrostatic attraction. They are also good conductors in molten or aqueous state, but not solid state, because in solid state there is no mobile charge carriers. They are hard and brittle because if you were to displace one layer from the other, there will be repulsion, so you can never push them back together, right? And lastly, they are soluble in polar solvents, but not in non-polar solvents. Polar solvents because formation of ion-dipole interaction, right? Non-polar solvent, you need energy to, if let's say you dissolve it in non-polar solvent, right? Na plus and Cl minus is not going to interact with your non-polar molecules, so there's no energy compensated to break the lattice structure, so that's why they won't dissolve in non-polar solvents, right? The next one is on ionic liquids, right? This is for information. You always see ionic compounds in solid form, but it can also exist in liquid form. Doesn't mean cannot. And why do I put ionic liquids? When you do the practices behind, you'll know why, right? If you were to flip behind, there are actually some questions on ionic liquids, right? This is just for information, so you can Google it or read it. That's your ionic lattice. Secondly is your giant metallic lattice. Metallic lattice is even easier than ionic lattice, right? They just consist of metal cations in lattice structure surrounded by your delocalized electrons. Properties: high melting point, boiling point because magnetic bond is very strong. Good conductors of electricity and heat because electrons can move about freely. Malleable and ductile because they can just slide over one another easily, right? And lastly, fourth is your giant molecular lattice, which is your diamond. They have a 3D covalent network of interlocking hexagons with each carbon being joined by covalent bonds to 4 other atoms, right? So it's tetrahedral in shape throughout. Bond angle 109.5. Properties: high melting point, boiling point, and it's very strong because a lot of energy is required to break covalent bonds. Poor conductor of heat and electricity because there's no free ions or electrons to move about. It is insoluble in all solvents because nothing can break the strong covalent bonds, right? Next is your giant molecular lattice for your graphite. Graphite is made of flat layers of carbon arranged hexagonally. Within each layer, carbon is bonded covalently to 3 other atoms using 3 of the valence electrons. The 4th valence electron is available for pi bonding, right? So if you were to look at the hybridization state, for graphite, each carbon is sp2 hybridized, but for diamond, each carbon is sp3 hybridized, right? This is perhaps the only thing that you never learn in O-levels, right? And between each layer, there are weak van der Waals forces. So only in graphite you will have a mixture of your intermolecular force as well as covalent bond, right? So as you can see from the diagram, I have good electrical conduction across the layer, but within the layer, but not across the layer, simply because the electrons is not delocalized across the layers, right? It's only delocalized within the layers themselves. So it has high melting and boiling point, same thing, large amount of energy is required to break the strong covalent bonds. Good conductors of electricity because of the free electron, right? Soft and slippery because the layers can slide across each other, since it's held by weak van der Waals forces, and it's insoluble in all solvents. Same reason as for diamond, right? So can you try this example? What's the term given to describe such? Should have learned, right?
Yeah, but forget.
Forget, huh? Do you still remember? It's called allotropes, right? Not isotopes, huh? Allotropes. So for example, graphite, diamond, carbon nanotube, Buckminster fullerene, you know C60, the buckyball, right? All these are allotropes of carbon, right? So which has a higher melting point? Graphite or diamond? Diamond? What's your answer?
Graphite.
Why?
Because it's sp2 hybridized.
Yes.
There's more S character.
Good. sp2, so the bonds are actually stronger. Okay? It's like a partial double bond. A lot of students say it's diamond because they think diamond is so strong whatsoever. So they say it's diamond, but no, it's actually graphite. Okay? Because all of these has partial double bond character. While for diamond is only single bond. Right? You can tell from, actually the hint is really here. You see that the bond length is 0.142, and this is 0.154. Okay? 142, why is it 142? Because it's sp2, that's partial double bond character, right? So graphite will have higher melting point. So the question C is with respect to your energetics chapter, right? So which one is the standard state of carbon, diamond or graphite? You learn energetics, right? Graphite, yes. Graphite is the standard state. Huh? which means for energetics, when you have CS, sometimes people specify it this way, CS, which is graphite lah. This is a standard state. So from this, then you will lead to other energy changes. It's not from diamond, it's graphite. This is stable by about, I think, 5 or 6 kJ per mole, right? So which has higher density, diamond or graphite? The answer is diamond, right? Why? If you were to compare the structure, right, which one is more compact? Take for, yes, it's diamond, right? Because
The bond strength.
the bond length, right? Apart from it, if you were to compare with graphite, between layers, it is actually 0.335, right, which is very, very much wider than what is stated here, right? So therefore, your diamond should have a higher density than your graphite, right? Let me just finish this page. So for a simple molecular lattice, one example is your I2 molecule, right? So low melting point and boiling points, because very little energy required to break the intermolecular force. Poor conductors of heat and electricity because there's no free ions or electrons. Soluble in nonpolar solvents and insoluble in polar solvents. This is your light dissolves light, right? So if let's say you have a nonpolar solvent, the solvent-solvent interaction is similar in strength as the IMF. Hence solvation is favorable. But for polar solvents, it is much stronger, so solvation is energetically unfavorable. Right? Now imagine let's say you dissolve I2 in chloroform. Okay? So this is I2. I just represent I2 this way. So this is your I2. So before that, between I2, there's very, very weak intermolecular force. Right? Between your chloroform, which is polar, right, there's very, very strong intermolecular force. If you want to mix them together, you have to break these strong forces first. And where do this energy come from? It has got to come from somewhere, right? But for this case, it's energetically unfavorable because this point is much weaker than this. If let's say you have a solvent, right, whose force is, intermolecular force is also this weak, then no problem, because the energy can be compensated, right? So that's why it's insoluble. And just for information, do you think, just for information, carbon dioxide also adopts this kind of structure, right? And just another question, do you think carbon dioxide can exist in liquid form? We will always talk about I2 sublime, carbon dioxide sublime, right? But can they exist in liquid form? Do you think possible or not possible? The answer is possible, right? But it doesn't occur at your atmospheric pressure, right? It can occur at some other pressure, right? So this is for information. 7th, lastly, is your hydrogen bonded lattice, only in molecules with FH, OH, and NH groups. So for example, in ice, each water molecule is hydrogen bonded to 4 other water molecules in a tetrahedral arrangement, right? Take note, only in ice, each of your oxygen is bonded to, if you were to count, 4 other hydrogens, right? If you were to look at the structure. So each of the big ball is connected to 4 of the small balls, right? So in aqueous form, it is H2O, whereby O is bonded to 2. In solid form, it is bonded to 4, right? So properties, lower density than water, because in water, right, H2O doesn't have a fixed arrangement, right? So it can be anywhere. So it's actually very, very compact, right? But for ice, they adopt a regular structure, right? And each of these regular structure contains a white space in the center, if you can see, right? So this white space actually contains nothing but just air, vacuum lah, right? So therefore, for ice, we say that their volume is higher than your water, which means that their density is also lower, right? So precisely due to this arrangement, your ice is less dense than water, and it also has higher melting point than other simple molecules, right? Because your hydrogen bonds are stronger than your IDID and PDPD. So if you were to compare this lattice with this lattice is going to be harder to break, because what's keeping them together is hydrogen bond, right? So the practices you can go back and try. Oh, you detach, it's okay. Right, you go back and try the practice. And next time, just doing this alone. Is it too fast to you? They go through too fast. Okay, right. So after this topic, do you want to continue with organic or do something else first?